All right, so good evening, and I hope you guys are ready for the class. And I'm just checking on my preview, so just want to make sure that it's working. All right, so it does look like it's working. We got 12 people watching right now, 13. All right, so I think people are starting to gather. All right, so I got some traffic already. Yes. Hmm. So we all get? Yep. All right, so I'm gonna close my preview. You won't see it anyway because it's on the side. And from last Thursday, I hope some of you have noticed that I have a new questions text channel under the category of text channel on our class server. So I hope you guys have a chance to take a look at those questions because it was based on a suggestion that you guys want to have more practice, more ways to apply the knowledge. So so that's what I've been doing, is to kind of throw in some questions, to kind of give you guys something to give your minds something to chew on. Okay, that's probably the best way to describe it, is to have it's basically exercise for your mind. Let's see, what is the time? We got about 1.5 minutes. So what we're gonna do today is to talk about binary subtraction, which is kind of like binary addition all over again, except the rules have changed a little bit. Okay, yes, I did say a little bit. Okay, it's really not a whole lot. So I'm just responding to people who who greeted earlier. All right. And we got about 30 seconds. I hope some of you have found the Beacon tutor to be productive, because I mean, we don't really get a Beacon tutor for this class very often, because not very often would anyone, kind of volunteer to become a Beacon tutor in a following semester. So there is that. And one of the things that I probably would do today is to show you the solution of the lab on last Thursday, because I think I got at least one question from one person to ask it. Let's see. Yep, that's binary subtraction right there. Thank you, Omer. So let me go back to that solution, which I'm not really sure whether I still have it or not, because I might have rebooted my computer between last Thursday and now. And the answer is, yeah, it's not, doesn't seem to be. Let me see. I might have saved it in a different location. All right. Okay, I got it here. So that would be a good starting point, because I want to show you how to get that particular homework, lab done, and kind of explain a few concepts along the way, and then we'll get started with binary subtraction. Good evening. All right, so it is time to get started. So here we go. All right, so this is basically what we had on last Thursday, and we need to finish up the circuit. That's what you guys did last Thursday. So at the beginning of the lecture, I gave you the file, and then at the end of the lab, you were supposed to turn in a 3 by 3 carry look ahead adder. So I'm gonna just kind of do the assignment, but I'm not gonna read my own instructions because I think I remember most of them. All right, so so the bottom line is we need to come up with the sum and also K3. So the sum is going to be a 3-bit wide output pin, and we'll just call it S for sum, and then we have a K3 over here. All right, good evening. So here we have a K3. All right, so this is how my mind works. Okay, I start with what I need to accomplish at the end, and then go like, okay, so how do we make this work? In other words, given what we have here, including all of this portion here, and also including the we want to come up with a sum and the overall carry of K3. What do I do? Well, there are actually 3 more things that I have here, which are K1, K2, and K3. So those items are actually really useful because that's how we calculate the carry bits for bit positions 1, 2, and 3. So the first thing I would look up is to find out, how is the sum term defined? Okay, and if you look up the notes, you will find that in general, regardless of the base, S subscript I is the R of Q of I and K of I. Okay, that's regardless of the base. Okay, it doesn't matter whether it's base 10 or base 2. And then we generalized. Wait, excuse me, I take it back. And then we made a specific case for binary numbers, base 2, because we can use logic gates instead of using arithmetic operations. So that is when we realized that we need to pull an exclusive OR gate. So we get to the exclusive OR gate, which is right here, and then we stash one here. So now we also need to make sure that this exclusive OR gate is a 3-bit gate. Now remember, we had one lab that only dealt with what is a multi-bit something. So it's basically a shorthand so that we don't need to use 3 individual exclusive OR gates. So we know that this is the result of an exclusive OR. So now the question is, what is it? What is this exclusive OR gate? Exclusive OR ring. Wow, man, that's a tongue twister right there. Well, Q and K, right? We talked about this earlier. So the first thing is a lot of people, at least initially, made a mistake. Okay, so I'm gonna make the mistake here. So I got a K1, I got a K2, and I got a K3. Okay, there we go. All right, so a lot of people thinking, oh, since we have these components, let's merge K1, K2, and K3 using a splitter, and then and then feed that splitter into one of the 2 ends of this exclusive OR. That would not be correct. Okay, so let me just kind of explain why that is not correct. I think some of you know that already because you asked me during class, and some of you did not because I can see that for the submission that I can see it from the submission that some people did not know about that problem. So what we'll do is I'm just going to burn some time and wire this thing up incorrectly. So now we get a splitter, and we'll make sure it is a 3-bit by 3-bit splitter. So in other words, it's 3-bit wide, and it also has 3 split ends. Okay, so we'll make sure that we can break it up into individual bits like that. Except this time we don't want it to be a splitter, we want it to be a merger. So to turn it into a merger, we just have to rotate it. Now it is a merger. Alright, so we put it, maybe here. Yeah, it doesn't matter. Okay, there are a few places where we can put it. Alright, so some people do something like this. Okay, and so one goes here, and then one, oops, come on, there we go, and then one goes here, and then the third one goes to the bottom one, and then we take it put it into here. The other side just goes to a Q. So the idea is, hey, since we got this thing called a tunnel, might as well use it, right? So here's my Q tunnel, and we have to make sure that everything is 3-bit wide. So the Q tunnel is really just here to make things look nice. We don't really need to use a tunnel. We can just kind of grab this wire and then connect it all the way up here. But since we want things to look a little nicer this time, we'll just go ahead and do it this way. All right, so then we have to wire up K1, K2, and K3. So once again, there are multiple ways to do this, right? So we can either just kind of tap into this wire, which is the easiest way to do it, and then just have a K0 to also feed into these various things. So I'm just gonna do it this way because this is not too bad. Okay, it doesn't look too bad this way. This type of topology, the way that we connect the wires, is also called a multi-drop type of connection. And as we will see in this semester, okay, so that's because I kind of dragged it on, and it actually connected not only to the G input pin, it also connected to the K0 input pin at the same time, and that's why I ended up with that orange line. Using a little touch point on a Lenovo keyboard to kind of draw this type of diagram is not really the best thing to do, but it works, so I'm not gonna complain. Yes, so you can complain that I'm not using the tunnels, but I'm just kind of doing this in a hurry. Oh, okay, so it's gonna look uglier. It's just that it'll still work. It just looks kind of ugly. There we go. And there we go. Okay. So now we have K3. So this is kind of like dangling by itself. But since this circuit here is also having the same name of K3, we will just go ahead and hook it up like this. Okay. All right. So a few people turn in something like this. Okay. At least logically, it is connected like this. Then you have to ask the question: how is this bit here? Okay, bit 0 of the sum computed. Well, it's coming out of exclusive OR. Okay, that's so far so good. But which bit are being used? Which bits? 2 bits. Okay, which bits are being used to compute as 0? From the Q tunnel, okay, that's okay. Look at the Q tunnel, and the Q tunnel comes from here, and that is coming straight from X and Y are just the original 3 bits. Okay, fine. So Q0 is used as one of the components to compute S0. All right, not a problem. The problem is on the other side. What about the K's? Well, we can see that K0 does not feed into this merger at all. What is at quote-unquote bit position 0 is actually K1. So that's why this way of hooking up is not going to work. So exactly, K1 and K0 are not the same thing. So Chris typed in the text channel, and he is correct that they are not the same thing. So now the question is, how do I fix this? Now, obviously, to some people, the first question is, so how many points am I going to lose? I mean, this is a lab assignment, okay? It's not going to be that many points. It's much better to make this mistake now compared to not knowing this problem and then make this kind of mistake in the exam. All right, so K1 goes to bit 1, and then K2 goes to bit number 2. Oh, okay. Doesn't work the other way. It has to start with a wire, and then bit 0 needs to go here. This is bit 0 right here. There we go. Now we got it. All right. Oh, my camera is blocking. Okay, so let me. Okay. I'll move this whole thing down a little bit. There we go. All right. So this is the correct diagram, And I got some questions about, so how did you know about using an exclusive OR here instead of an OR? Well, it has to do with, S is computed using the R function, and the R function, um, when we are using, okay, so for base 2, the R function is exclusive OR. That was actually in the modules, and that's why I use an exclusive OR here instead of an OR. And that's, I think that's really the simplest way I can answer that question. Why did I choose to use an exclusive OR instead of a regular OR? So I cannot overemphasize the importance of reading the modules. In other words, everything in this diagram really comes back from they really come from the module. The module, the written the module has everything that you need in order to complete this circuit here. And the material is already discussed last Tuesday, not last Thursday. Last Thursday was when we applied that knowledge, but the knowledge was actually introduced in lecture on Tuesday. So I cannot overemphasize the importance of reviewing the material and all the things that I have been suggesting, since the beginning of the semester. So are there any questions about this assignment? Oh, one more thing, since I'm kind of nagging already, might as well, nag a little more. The circuit tester is given to you so that you can test the circuit before you turn it in. A bunch of people did that. Okay, a bunch of people, direct messaged me and go like, okay, this is what it's supposed to look like, and this is what I'm getting, and they're different. Okay, what is wrong with my circuit? So I, basically look into those circuits and I responded to those questions. And then there are some people who did not, right? There are some people who did not use the circuit tester at all and just turned in something like, before I, corrected this diagram here. The circuit tester would have caught it like that, okay? And that's why I provided the circuit tester. So I just want to point out resources that are already available to you, and I would recommend people to realize those resources and use those resources. All right, we got a few people typing, and unless we have questions about this, we can move on to subtraction. Ooh, I almost touched my USB connector. Huh? Yep, there you go. Uh-huh. Why is the order dependent? Well, let me see. So let's magnify our splitter here. See all these numbers here? 0, 1, and 2? Why do you think those things are significant? What are they indicating? This is indicating this Y here is becoming bit 0 of this bundle of wires. This is bit 1. This Y becomes bit 1 of this bundle, and this becomes bit 2 of this bundle. Bit position, exactly. So Taylor is right. It is because it indicates the bit position. Now, can you scramble things and not make it look this regular? Can you make it look kind of weird, like 0, 2, and then a 1? Absolutely. You just have to feed the bits accordingly. So bit 1, K1 still has to go to bit 1. K2 still has to go to bit 2, and then K0 still has to go to K0. You can scramble the position all you want in the splitter, but in the end, it really has to do with how this exclusive OR is computing the sum bits. Okay, so bit 0 of the sum needs to utilize Q0 and K0. Bit 1 of the sum needs to make use of Q1 and K1, and then bit 2 of the sum needs to make use of Q2 and K2. As long as you can make that happen, yeah, sure. I mean, if you want to have a good time, just kind of scramble things up a little bit, fine. Go ahead and scramble them up. Okay, it doesn't matter what order this looks like. It just has to do with bit 0 goes to bit 0. Bit 1 goes to bit 1, and bit 2 goes to bit 2. I'm not sure whether I'm answering the question or not, but I mean, that's kind of what it is. Now, if you guys say that, but Tag, the way you explain things is just making it worse, you can go to help, go to library reference, And I have introduced this resource from what? The first class. And then we go to, let's see, splitter right there, first item. And it explains to you how a splitter works. Yes, it is kind of long. I'm not going to read it. No, no, I did not say that at all. No, I did not say that. I did not. I don't even remember what I said. Okay, but I certainly would not say something like that because I am not a how should I put it? There's a term for those people. Damn it. Yes, I said that word. There's a term for these people. They're called no, 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 no. That's not the term. Infidels. I'm one of those people. I'm one of those infidels. Yes, infidels do not believe in. Yeah, exactly. That's my point. With that being said, I might be a believer of the FSM, the Flying Spaghetti Monster. You can look that up. Alright, so enough fun about religion. And we're going to move on to subtraction. Alright, so are we good here? Maybe. uh, I think it's an implant, so you guys cannot see it. Yep. That is funny. I like John's comment. Alright, cool. Alright, so now we're going to move on to subtraction. So subtraction as a module, maybe I'll save it. Save as, and we'll make it a different name. So we'll put it into my documents folder. Yeah. Okay, I'll put it here and then move it later. There we go. Alright, so now we're going to talk about subtraction. So subtraction is really boring because we have already talked about addition. So subtraction is like, that's not a whole lot of new stuff to talk about. So I am typing, on this side so that you guys can see the rendered result on this side over here. All right, so the first thing we talk about is single digit subtraction. Okay, so single digit subtraction is basically looking at, this is all in base 10. Okay, so I'm going to emphasize this is in base 10. So in base 10, when we think about, what is 2 minus 7, then you guys will go like, no, that's not what I intended to do. All right, so okay, now we need to get rid of that too because it basically repeated what I typed like 10 times. I accidentally typed 10 and then do the insert. So in VI, that's like repeating an action like 10 times. All right. So 2 minus 7 is a single digit subtraction because 2 is a single digit in base 10, 7 is a single digit in base 10, so this is a single digit subtraction. The question is, what is the result? Okay, and you guys will go like, oh, we understand negative numbers, this is negative 5. Well, that's one way to put it, but how do you do multi-digit subtraction? Well, when you need to do multi-digit subtraction, then you need to break it up and you say the single digit difference is, let's see, this is not a very good example. Let me change the number up a little bit, and this is 3. Okay, so 3 minus 7, the single digit difference is not negative 4, and instead it is 6. And then there is a borrow of 1. So this is how you perform your multi-digit subtraction, is when you have 3 minus 7, you write it as a 6 as a result, and then you put a 1 on the next column, the column to the left-hand side, to remember that I just borrowed 1 from that column. So is that okay? Does everybody understand what I mean by a single digit difference, and also what I mean by a borrow in a multi-digit subtraction scenario? So I'm waiting for confirmation of that before we move on, because otherwise we might need to explain that a little bit. So we're good? Excellent. All right. Excellent. Very good. How is that 6? Because so the problem is not just 3 minus 7. Well, this is an example. Okay, so let me give you guys another one. Just see if you guys understand the concept or not. What about 2 minus 8? So in this case, what is the single digit difference? It is 4, because we have to borrow 10, right? After you borrow 10, it becomes 12. 12 minus 8 is 4. What about the borrow? Do we have a borrow of 1? Yes, we do have a borrow of 1, so we put a borrow of 1 over here. So does that answer the question that was asked earlier? Are we good? All right, cool. Excellent. Let's try one more time. Okay, so let's try 8 minus 2. Okay, so what about 8 minus 2? What is the single digit difference? In other words, if you have a multi-digit subtraction and you turn out to be looking at 8 and then 2, what number would you write down right below the 2? 8 minus 2 is a 6, right? Yep. All right, so excellent. What about the borrow? Do we have a borrow of 1 or 0? Okay, you guys are smart. Okay, you already knew that I would ask about a borrow, and you just typed the borrow right away. Excellent. Okay, so I think we're getting the idea. Okay, so I am just going to use a notation. So I'm going to use the confusing thing, which is the r of xy, as the single digit difference of x minus y. Now, the reason why I said this is kind of confusing is, well, didn't we define r as the single digit sum in addition? Yes, okay, we actually did. So I am actually reusing the symbol here, which is kind of confusing because they are not the same thing, are they? Right? Because 2 plus 8, okay, has a single digit sum of 0, and now it has a single digit difference as 4. So they are not the same. Okay, so I'm just borrowing r for the time being. And then we're going to define b of xy as the borrow of x minus y. X has to be a single digit, y has to be a single digit, but this actually applies to any base. Okay, so we'll just go ahead and kind of deal with that kind of ambiguity for now. Why did Tech use the same symbol r when he could have used something else? Okay, so there's a reason, but we cannot see it yet. So right now I'm going to define a C function for r. So we'll say unsigned. Okay, it's important that we're dealing with unsigned here, because when you look at the single digit difference, they are all non-negative. When you look at the borrow, they're also all non-negative. So that's why I'm going to use unsigned as the type of the function. So this is r, and then we have unsigned x, unsigned y. And we have to return a value. So we have to return something. So now the question is, how do I write the r function here? What value should it return? You guys remember that we did this once for addition, right? So now we're doing kind of the same thing with subtraction. So what would that look like? In other words, if I say x is 3 and y is 7, how do I get to 6? If I make x 8 and y2, how do I get to 6? Again, okay, so because they both return a value of 6. So how do we do this? Oh, there are a few ways to do it, right? I mean, you can always check to see if one is less than the other one. If so, you do it in one way. If not, you do it the other way. But you already know that, I'm too lazy to make, special cases like that. So there's no need to make a special case because all you have to do is to say, x is a single digit, y is a single digit. As a single digit, neither can exceed 10, right? Yep, exactly. So Bernard has got the right idea. Okay? No, you got it. Bernard, you got it. Okay? You add 10 to the first one, which is x, and then you subtract y from the sum of 10 and x, and then you go like, but what if x is greater than or equal to y? Guess what? We can just mod the result. Okay? So we can say something like this. Okay? 10 plus x, the whole thing, minus y, and then take this entire thing and then mod it with 10. That will get the job done. I mean, you guys can plug in the values and you make sure that it does work. So let's plug in some values, okay? Because I don't trust myself. Sometimes I think I have a solution and then I just go like, oh, that didn't work. All right, so let's check it. 10 plus 3 is 13. 13 minus 7 is indeed 6. 6 mod 10 is still 6, okay? Not a problem. What about this one? X is 2. 2 plus 10 is 12. 12 minus 8 is 4. 4 mod 10 is also 4. Works out for the second test case. What about the third test case, which is when x is not less than y? So we got 8 plus 10, which is 18. 18 minus 2 is 14. But 14 mod 10 is, no, I take it back. I take it back. My arithmetic is awful. So 10 plus 8 is 18. 18 minus 2 is 16. Sorry, excuse me. So 16. 16 mod 10 is 6. So it still works out. Okay, so this is going to work out for all cases. Now you can say, but Tech, this is not the quickest way to get things done. Well, it kind of depends on the architecture. If you have an architecture where there's there's hardware division, yeah, this one is pretty fast, say as fast as any other approach. On the other hand, if you have a processor like an AVR, which is utilized by Arduino controllers, then it does make a difference, okay? But we are not going to talk about optimization at this point here. We'll just kind of settle with this solution here. All right, so now that we know the R function, what about the B function? The B function is actually easier, okay? So B of unsigned x, unsigned y. All right, so how do we specify the return value here? So what are we returning? So it looks like we return a 1 if and only if x is less than y, and we return a 0 otherwise. So some people may say, oh, okay, we can just return this. Nope, right? We talked about this already because in C++, okay, well, this is C, not in C++, but if it works in C, it's going to work in C++. That's kind of the idea. So anything that is true is basically a value other than 0. There are many values that are unsigned and they are zeros. They're ones, sorry. So any non-zero is basically a true. So we are going to have to say, yeah, we better make sure that it's returning a 1 or a 0. So question mark 1 colon 0. I'm getting distracted because my watch is buzzing me because it is time to take roll. So let's go ahead and take roll. Today is 028. I'm just gonna unhide it and then I'll show you the answer. And the answer is overflow. I will copy and paste it. There we go. So just copy and paste into the answer and we are done with taking roll today. All right, so I'll give you guys a moment. And for those of you who have taken row already, typed in or copied and pasted the word overflow, let's get back to the borrow function. Are there any questions about why I need to use a ternary expression here? Why I cannot just return x is less than y? Okay. All right, we got a few people typing, which is good. That's always a good sign. All right, so for when I'm using, yep. Did you just say that any number other than 0 is true? That's right. Okay, that's what I said. Because in C and also in C++, an integer value that is other than 0 can be interpreted as true if the context wants a Boolean. So that's why, if I just return x is less than y, this expression here is just going to get it, if x is indeed less than y, okay, this expression is just guaranteed to be a non-zero value. So the question is, if I have a 32-bit unsigned number, how many non-zero values do we have? The answer is about 4 billion, okay? And 1, the value of 1, is one of the 4 billion. I have no idea what what kind of code the compiler is going to generate. So there's no guarantee that x is less than y is going to return exactly 1 when x is indeed less than y. Now, if it is not, we're guaranteed that it's going to return 0. That is not a problem. The problem is if it is true, we are not guaranteed that x is less than y is going to return a value of 1. And that's why we have to force it to return a value of 1 by the use of this ternary expression. I think it is compiler dependent, and I would say most compilers that make sense probably would use 1 to represent true, but since there's no actual guarantee to do it, I would much rather not to depend on it. Yep. So that's really just kind of good programming practice is not to make assumptions that is not a part of the standard. All right, so now that we have this, okay, are we okay with this? Are we kind of convinced that the R and the B function are now done? For base 10 anyway. Okay, good. So we got a few confirmation. So now we want to extend these definitions to, well, thank you. So now we want to extend these definitions to base 2. So we will say in base 2, okay, we'll make it a bulleted list item. Oh, okay, my cursor is at the wrong place. There we go. Oh, still at the wrong place. There we go. Okay, so in base 2, we are going to do exactly the same thing, right? This is how most people write their code when they are not very experienced, is copy and paste. There we go. We like to copy and paste, and then we just go like, oh, everywhere we see 10, which is the base, we change it to 2. Oh, no. Okay, 2 plus x, and then we also have to change this mod to mod 10 to mod 2. The other one doesn't even refer to 10 at all. Okay, so we change this 10 to a 2, we change that 10 to a 2, and then this one does not even need to know what base we're dealing with because we are just looking at the single digit x and ask, is that less than y? If it is, return a 1. If it is not, return a 0. All right, so that seems pretty easy, right? Except we have a problem. The problem is, well, these are all involving arithmetic operation, and we're trying to figure out, the circuitry to perform arithmetic operation. That doesn't work, right? This is like a circular thing. In order to do something, we have to figure out how to do that something. That doesn't work. Okay. So if that doesn't work, what are we going to do? We're going to use the same technique that we have already used in addition, in binary addition, which is basically just to spell out the entire truth table, because everything in base 2 is just true and false. 0 is false, 1 is true. So we want to spell out the truth tables and see if we can recognize something, right? So that's what we're going to do next. So we have x, we got y, we got r of xy. I'm not going to use equations here because it's just extra typing that does not need to happen. This is borrow of bxy, and then turn it into a table. X can be false, y can be false, and if that is the case, the single digit difference of 0 minus 0, we plug in those values. Don't even try to think about it, okay? Just plug in the values over here, okay? 2 plus 0 is 2, 2 minus 0 is 2, 2 mod 2 is a 0. So r is going to be a 0. What about b? 0 is less than 0 is false, and we're going to return a 0 over here. Alright, first row is done. What about if x is 0 and y is 1? Once again, don't think about it, okay? Just plug in x and y into the functions and let the functions do the work. So 2 plus 0 is 2, 2 minus 1 is 1, 1 mod 2 is 1. Alright, so the r value is 1. What about the borrow? We have x being 0, y being 1. 0 is less than 1 is true, so it returns a 1. There we go. And then we have 1, 0. Okay, so x is 1 and y is 0. Once again, don't think about it. Plug in the values, right? Because we already know these equations work for any base, so might as well just plug in the values. So we got 2 plus 1, which is 3. 3 minus 0 is still 3. 3 mod 2 is 1. Alright. And then we look at this part over here. 1 is less than 0 is false. So we return a 0. There we go. And then finally we have 1, 1. So plug it in. 2 plus 1 is 3. 3 minus 1 is 2. 2 mod 2 is a 0. And then we have 1 is less than 1 is false, so we return a 0. And there we go. We got the truth table. We look at this. And do we have any questions about why I chose the name R, even for binary subtraction? Alright, so I'm going to send... Okay, I shouldn't say that. Let me... Okay, never mind. Never roll back, okay? Never mind I said that. 3 mod 2 is 1 because what is mod again? Modulus, yes. Okay, and in terms of normal division terms, what is it? Remainder, very good. Okay, so it's the remainder of 3 divided by 2. There we go. All right. So did I respond to that question? Or I should ask, are there any other questions about why 3 mod 2 is 1? Are we convinced that 3 divided by 2 has a remainder of 1? You got 3 candies. You have 2 kids to evenly distribute those 3 candies. After giving each kid 1 candy, you have 1 candy left in your pocket. That is your remainder. Alright, so that question is done. Alright, excellent. Well, in that case, in the case of mod, the first part is your dividend, and then the second part is your divisor. So it is useful to remember those terms in arithmetics. All right. Anyway, let's look up this column here. Okay, r of xy. Now, given the same values xy, and looking at rxy, haven't we seen this before somewhere? Where did we see this last time? Or is tech just delusional that we have seen this before? Exactly. In binary addition, the single digit sum is exactly the same. And it is also exclusive OR. Very good. Okay, so we are making connections now. Excellent, excellent. So now we can say, oh, okay, so from this, we can see that R of xy is really the same thing as x exclusive OR with I. Okay, so if you want to put in that exclusive OR symbol, it is called O plus in LaTeX. It looks like a plus, but except it has a circle around it. But if you prefer not to use the special symbol, you can always say this is just x, and then I'm going to use this just so that it doesn't it's so that it's not italicized. So it's x exclusive OR with y. All right, and we also have some other way to do the same thing. Okay, so but it's the same thing. Okay, the bottom line is whatever R function that we used for binary addition, we can just use the same thing here for binary subtraction. So what about B? B doesn't look the same as C. Okay, so how do we express C? I mean express B. So B of xy, it looks like the only time the value of B function is going to return a 1 is when x is a 0 and y is a 1. Yep, so Owen has gotten it right. So it is basically take the negation of x and then do a conjunction with y. And this notation is something that we have already been using for a while, but it is important to also know that the negation applies to x first, but it does not apply to y. So negation only applies to whatever is immediately to its right hand side, and it has the highest priority compared to all of the other operators. So kind of remember that part when you're reading these shorthands of Boolean expressions. Okay, so we are looking at this and go like, I think we can do this with a gate, right? I mean, we just did today. I just did it at the beginning of the class today. Exclusive OR is a gate. Oh, okay, that's good. What about this one here? Negation is a gate, right? And then conjunction is a gate too. So we can do both of these using logic gates. So now, okay, this is the moment where I really want you guys to make connections all the way to the beginning of the semester. This can be done using transistors, okay? Because even if you don't like, okay, if you don't like exclusive OR and say that we have never talked about how to do exclusive OR using NAND gates, fine, do it the longhand way, okay? So the longhand way to do this is not x and y, or x and not y. The parentheses are really not needed, but I'm just putting those in just so that we can see that we take the result of the two conjunctions and then OR those two conjunctions together to become the actual end result. So in this form, negation can be done using NAND, and can be done using NAND, or can also be done using NAND. So now we can look at this and go like, yep, we can use logic gates and transistors to implement binary subtraction. Alrighty. So now let's go through a few examples, okay, just so that we understand how this works, okay? So to go through the examples, I'm going to do about the same thing as last time. Let's do 3-bit by 3-bit again. Okay, so we have bit 2, bit 1, bit 0. And then the second row is going to give us the first number. This time, it's kind of important to indicate this is. Oh, I have to change this to header first. Sorry about that. All right, because otherwise it won't look like a table. All right, and this is our x. It doesn't look like what I want it to look like. What am I missing? Oh, right? Okay, there we go. So we're turning this into a table, and let's say we have 0, 1, 0, and that's our x. And then we are subtracting from x, the value of y, and y turns out to be, let's do this one, 0, 1, 1, and this is our y. So in this particular subtraction, x is also called the minuend, minuend, and then y is also called the subtrahend, subtrahend, subtrahend. And let's find out what the first row is gonna be. And we have our familiar Q. Q is a row, and then we have a not so familiar but similar to what we have seen before. I call this one T, which is taking the place of K, which is carry, right? But this is subtraction. We don't have carry in a subtraction. So T is coming from the word take, okay? Yes, that's my term. And D is for difference, okay? So we have about the same kind of setup in terms of the structure as a binary addition, except this one is for subtraction. And we have Q exactly the same way as before. It is just the exclusive OR between X and Y. And then we have T, which is the take, kind of the carry. And then we have D instead of the sum. So let's go ahead and figure out the structure first. Okay, how are these things defined? Q of I, okay, this one is no surprise. Q of I is the same thing as R of xi, yi. And if you want to use exclusive OR, yeah, we can just use exclusive OR here. This is O plus y underscore I. There we go. So that part seems exactly the same. It is exactly the same as binary addition. Let's take a look at the next one. The next one is T of I plus 1. So T of I plus 1 is here. So we are going to take a look at this subtraction. Let's go ahead and fill in first, okay? Because I want you guys to have a chance to actually work on this. 0 minus 1 is a 1 with a borrow from the next column. Are we okay here? And then we assume T0 to be a 0, much like in a normal addition, we assume K0 to be 0. So in a normal subtraction, we are assuming T0 to be 0. And then we have 1 minus 0 being 1 down here. So we put a 1 here. So it is important, right now it's important to understand why we have a 1 here. This 1 is because 0 minus 1 is having a borrow of 1. And that's why we have this 1 over here. So now we're going to subtract, we have 1 minus 1, which is a 0. So let's put that 0 into the table. And then we have 0 minus 1, which is a 1 with a borrow of 1. So now we end up with a 1 as the single digit difference between the Q and the T. But we also have a borrow of 1 from digit 2, sorry. And then we have 0 minus a 0, which is just a 0. So we put a 0 here. 0 minus 1. Okay, let me point out which one. 0 minus 1 is a 1 with a borrow of 1 over here. So we have 1 and a 1 over here. Do we have any questions about what I just did? The actual example of binary subtraction using the rules that we have just kind of talked about. Alright, so as you guys are trying to answer that question, I'm going to finish typing how T of I plus 1 is defined. It is the borrow of xi, yi, or the borrow of qi, ti. Alright, so we got. So is there a bit position 3 for row T? Yes. So this is supposed to be bit position 3, and you are right. There should be a bit 3 position for the for row T. That is correct. Thank you, Chris. All right, and one more definition and we are done here. D of I is the R of QI TI. There we go. And that's it. This is it. Okay, for those of you who still prefer to look at things, from just using negation, conjunction, and disjunction, we can just kind of rewrite this, the longhand way, which is not xy or x not y. There we go. All right, so now we look at these definitions and we look at this and go like, that is confusingly similar to something that we have seen before. In fact, it is exactly a week ago that we have seen something like this, but not exactly the same. Do we see the similarity between how we use the T term versus the K term from binary addition? It's just that, oh, instead of C over here, we got B over here. And in addition, do we see how the D term is kind of like the S term, except instead of using K over here, we're using T over here? Other than that, other than just substituting certain letters with some other letters, the differences seem to be pretty minor. I mean, the only real difference here is how B is defined. B is not xy instead of just xy. Carry is just xy or x and y. Borrow is not x and y. That seems to be the only difference here. Is that right? Apparently so, right? Okay. So if this is the only difference, okay, that means most of the things that we understood about binary addition would also apply to binary subtraction. In other words, we might be able to use the same kind of derivation and figure out how to get this done, figure out the relationship of the entire subtractor. Okay, so we have already done the adder. Now we want to deal with the subtractor. So now I'm going to go to binary number subtraction and take a look at this particular module. And you can see how this module is way shorter compared to the module for binary addition because most of the things are the same. Okay, the only differences is how about that propagation? How about that carry look ahead thing? How does it become borrow look ahead? Yep, minor changes. Yep, Brian is correct. So what we're gonna do is to do something crazy again. We look at a T of I plus 1 being the B of xi by I or B of qi ti. Okay, so that we have seen already when I talked about it here, right? So exactly the same thing. The question is, but Tack, didn't you talk about something like if T of I plus 1, depends on T of I, then the whole thing has to be daisy chained and the amount of time it takes to finish the calculation is going to be proportional to the number of bits that are involved, and that's going to be slow. Well, the answer is yes. Okay, we saw the same kind of problem when we talked about binary addition. So the question is, can we apply a similar technique and implement borrow look ahead here instead of carry look ahead for adders? So that part is a little bit kind of tricky because now we have to see if we can have a similar derivation to end up with something that we can use, something for P and something for G. All right, so I'm going to quickly, go over the Boolean algebra stuff, here. So the first line to second line is just by definition of B. So B of xi by I is not xi and yi, and similar for the other one. So that's really just applying the definitions of the B function. From the second row to the third row is, let me see here. Oh, that's how Q is defined, because Q of I is xi exclusive or with yi, which is also seen as xi and not yi or not xi and yi. And then from here to here, I used, let's see, De Morgan's law. Okay, so this is De Morgan's law going from the third to the fourth row. From the fourth to the fifth row is, let's see, it's De Morgan's law again. So this time I'm distributing this negation into this conjunction, ending up with this disjunction, distributing this negation into this conjunction, ending up with this disjunction here. So that's also De Morgan's law. From this to here is FOIL. Okay, so just like you have FOIL in normal algebra, we also have FOIL in Boolean algebra. Works exactly the same way. Okay, so we have FOIL. And then from here to here is simplification. Not xi and y, not xi and xi is guaranteed to be false because it's a conjunction of one thing and its negation. So one of them has to be false, and we need at least one side to be false for the whole thing to be false. So it's guaranteed to be false here. Same thing over here with yi and not yi. It is also guaranteed to be false. So from here to here, we're just simplifying, because if you have a disjunction and one of the components is known to be just false, then you can just get rid of that component because it's not going to change the value of the overall disjunction expression. So we just drop the two zeros here. And then from here to here, I have and one or and true, added to this expression over here. And then true or whatever is always just true, so I decided to say true or ti or ti. Okay, it doesn't change because once you have a true in a disjunction, then the entire disjunction is guaranteed to be true no matter what else you introduce into the expression. But I do this for a reason. So from here to here is distribution. So the first term just has not xi and yi, and then the other two terms now has the extra term of ti added to it. That's just distribution. And the other side also goes through distribution. And then from this row to this row here is just reorganizing things a little bit. It's based on commutative law, which means we can reorder things within a gigantic disjunction and it won't change the result of the disjunction itself. And then from here to here is factoring, which is the reverse of distribution. So I apply that twice within this, and okay, so these two terms become this term over here, and then these two terms becomes this term over here. And then from here to here I apply factoring again. Okay, so same thing over here. So I apply factoring one more time. I could have combined the two factoring into one thing, but I did not. So two separate steps of factoring in this case. And then we have simplification, because yi or not yi, one of them is guaranteed to be true, and in a disjunction, if at least one side is true, the whole thing is true. So that's why this disjunction is guaranteed to be true, and same thing applies to this one over here. And then true and whatever is always just whatever, so I just drop the two i's. They are no longer needed. And then one more factoring, and I end up with this one over here. So once again, in this class, you don't need to derive in Boolean algebra, but it is probably useful for you to understand Boolean algebra just in general in computer science. Okay, so even if someone is to tell me and say, but I just want to be a game programmer, I don't want to be a computer scientist, do I still have to understand Boolean algebra? What do you guys think? If somebody just wants to be a programmer, does that person still need to understand Boolean algebra, and why would that be? Because they're going to get a crazy boss like Tech who's going to walk over to the cubicle and just kind of drop a few Boolean algebra puzzles every day and go like, I want you to solve this in like 3 minutes now. Well, not really. Okay, so the reason why Boolean algebra is important is there are different ways to express exactly the same condition. So that means when you go in and you're reading somebody else's code, okay, and you encounter a conditional statement, if then else, or a loop with a condition and stuff like that, you kind of have to understand what that condition is. Okay, what does it mean with this particular Boolean expression here? So you have to understand Oh, so that means blah blah blah, because that's Boolean algebra right there. Because the way you would have expressed the same thing may not be the same thing as what the other programmer did in the existing code. So understanding Boolean algebra would allow you to transform existing code, existing expressions in a program into a form where you are familiar with, or at least you can compare two conditions in the code and go like, oh, these two things are the same. Okay, that is important when you become a programmer. All right, so that's the importance of Boolean algebra. All right, so here we go again. A very well hidden definition of terms. It's a very short single line double sentence type of paragraph, but I'm redefining G and I'm redefining P. So in addition, G of I is xi and yi, and in binary addition, P of I is xi or yi. So in binary subtraction, we negate the xi first in both cases. So G of I becomes not xi and yi, and the P of I becomes not xi or yi. Oh yeah, yeah, yeah. For games, games are the worst when it comes to double checking conditions and what the user is doing, what the sprites or objects are doing, and so on. There are many conditions to check, like what is colliding with what, and so on and so forth. Yep. So Bernard is correct, 100% about how these things are particularly important in game programming. All right. So getting back on topic here. So once we define G of I and P of I this way, we look at this expression and go like, hey, this is the same thing as G of I, and this thing here is just it's the same as P of I. So now we can re-express this earlier thing, okay, that looks kind of messy like this, into something that looks awfully familiar as T of I plus 1 is now G of I or P of I T of I. It's like, we have seen this one before somewhere. Where have we seen this? There's only one difference. The way we saw this last time, there's only one little difference. The T was K. And that was it. That was the only difference. So using the very same technique as last time, we'll now be able to generalize. If you want to calculate T of n plus 1, this is how we do it. And then somebody's going to say, Patek, you never explained these notations here. What is the big V and the big, inverted V is doing over here? Well, that's one of the questions in the questions channel. So let me go back to that one and see if I can put a link here. Okay, let me see. That should stand out. Yep, there we go. It's called Big V. So if you go to the thread called Big V in the channels, let me see if I can just make a link out of this, because that can be useful. And let's see. Copy ID. Okay, I can copy ID, but I'm not really sure whether that's going to show up correctly here in the text channel or not. No, it just gives me a bunch of a bunch of digits. So you guys just have, okay, let me just do this. This is a whole lot easier, right? Screen capture. So go to questions, and once you get there, go to the one that says Big V, which is up there somewhere. Oh, I think I just moved past it. Oh, come on, where is it? There you go. Okay, so this is the one. And if you read the answer or the thread corresponding to this, that tells you how to read the Big V notation. Oh, thank you. Okay, somebody figure out. Okay, I am not savvy with Discord. Good job, Taylor. Good job. Thank you. There we go. So now everybody can link to that definition, and now we understand how the Big V thing and the big inverted V thing works. It's kind of like sigma, okay? Where sigma applies to the arithmetic sum of a series of values. This is just kind of the same thing, except is applying disjunction or conjunction to a series of values. So there is that. Okay, in other words, you can write a loop to do all of this. Okay, it just looks kind of hairy, but it's not really that bad. It really is not. It's just a nested loop here. You have one loop. This is the inner loop. This is the outer loop. You can see how the index of the outer loop is I going from 0 to n, and then the inner loop has an index of j that basically takes the value of I and say, okay, it's only going from I plus 1 to n for the value of j. So you have a nested loop on this side. This side is not even nested, it's really just a single loop where you have I going from 0 to n, and you are ANDing all the pi's together and then ANDing t of 0 as one of the last thing to throw into that conjunction. So I would suggest that you try this out, okay, with the K1. So try it out with K1, okay, you go like, but K1, isn't K1 kind of trivial? The answer is yes, it is trivial. However, this formula should still apply, okay, so try it out with K1 first, and then try it out with K2. So in the case of K2, n equals to 1, and plug in n equals to 1 for all of these, and see if you can end up with exactly the same formula for K1 in carry look ahead, and then K2, okay, and if you want to be adventurous, try out K3, okay, it's really not that bad. I mean, once you figure out, oh, so this is really just a loop, I just have to kind of append these things, one after another, and I think many of you probably recognize that pattern already. You just did not have the vocabulary to express that pattern. And that's basically all this is. Okay, it's just a notation to express the pattern that many of you probably already recognized when we expanded and also derived the formulae for K1, K2, and K3. Many of you probably already look at that pattern and go like, oh yeah, this looks kind of repetitive. I think I can figure out the next one. That's basically, this is just a generalization of that. Alrighty, so do we have any questions at this point? We got about 11 minutes to go in today's lecture. So I still have some other items that I would like to talk about, but I want to kind of pause here and see if there are any questions. We are not going to do that because it's too easy. I know some of you are thinking, oh man, you never give us something easy to do. Well, what you're going to do is actually not too bad if you have read ahead of time or if you pay attention in class today. I mean, it really is just kind of a repetition of what we did today. But what I would do is to give you an answer to what a binary subtractor would look like, okay? Because some of you might want to see that, right? So that's exactly what we're gonna take a look at. Okay, so we'll first of all, I'm going back on the side of the screen here to the circuit that we worked on earlier today. And obviously I cannot remember where I stashed it. Okay, fine. LogicSim, you have to tell me where I stashed that file. Oh, right, it's right here in my home folder. There we go. Okay, so we're looking at this circuit here and go like, yeah, but Tack, this is an adder. It's not a subtractor. How are we going to fix that so that it becomes a subtractor? Remember, all we have to do is to negate x before we get it into the OR gate to become P, and we negate the x before it becomes G. That's all we need to do. That's all we needed to do. There was nothing else that we actually need to do. Then you look at this circuit and go like, oh man, then we have to add some negation gates and whatnot. I mean, that's a lot of trouble. Nope, I tell you, it's easy. Okay, it's easy. So what we do is we first, okay, depending on how tolerant you are with things looking really kind of ugly, You can probably not even do this step here, but I'm gonna do it just because I think it's gonna look kind of ugly if I do it without. Okay, so I'm removing all the um, inputs, input wire from X into the OR gate to compute the P, and the AND gate to compute the G. The Q term doesn't change, right? Because remember, R is exactly the same as before, so we don't have to negate anything going into the exclusive OR gate. And I just hid my Discord screen. Let me pop it back up in case anyone is asking questions. All right. Okay. So let's go ahead and do some, kind of surgery over here. So I can even do this. Okay, this is really cool. So you can do a click and then a shift click. So now we have two gates, both selected. So what we do is we look at this row over here. Negate top, negate bottom. Okay, so we only need one to be negated. We only need to negate the top input pin. So that's how we do it. That's how we do it, man. So now we have the top input pin negated. This bubble here means negation. When did we learn that bubble means negation? From the first class. From week 1, the first class. Exactly. Okay, good job. You guys are remembering those symbols, the discussions. So now we just have to rewire the thing, because remember what I said, you can probably get away without removing the wires first. It just looks kind of ugly. Now we have a subtractor. That's it. That is it. Okay. Now we have a borrow look ahead subtractor. That's it. Just like that. Yeah. Yep, that's all the way back, Edgar. That's very good. That's it. Okay, so let's double check, making sure that this works, right? So we're gonna give it the example that we talked about today, which was what, 0, 1, 0 minus 0, 1, 1, I think. Yeah, so I think that's the case. 0, 1, 0, and then 0, 1, 1. And now it's a subtraction. See how we get a difference of 1, 1, 1 and a T3 of 1. Yes, I didn't change the label, okay, but you guys get the idea, right? I mean, sum is really the same thing as a difference, except one is for addition and one is for subtraction. And then K3 is for addition, T3 is for subtraction, but I have already changed the circuitry to perform subtraction instead of addition. This is it. I mean, when I first did this, go like, wow, that's easy. And I'm still amazed how easy it is to convert a carry look ahead adder. And you would think that, oh no, we're gonna have to redo all of those, K1, K2, and K3 subcircuits. Those things are messy. As it turns out, we don't have to do a single thing about K1, K2, K3. We just have to change the way we compute P and G. And the only change that we have to do here is to negate X first. That was it. Okay? That was it. All right, so we got about 5 minutes left. Okay, plenty of time to talk about the very one last thing I want to talk about. So this has to do with overflow, and that's why we have overflow as the word for row taking, is because it's one of the topics that I kind of want to talk about. It is actually defined in the lab itself, so if I don't talk about it, it's no big deal. It's already in the description of the lab. However, since we do have time, I'm going to talk about it. So overflow is uppercase O, so this is not 0. This is actually uppercase O. So overflow is defined to be, so let me give you some additional information first. Okay, so for a n bit subtraction, overflow is defined as follows. Okay, it's defined as the negation of x subscript n minus 1. Let me see, this is for subtraction. Okay, right. So y underscore n minus 1, and then d underscore n minus 1. Or, let me see, does that make sense? Okay, let me close the whole thing first, so this way it looks better. Alright, so we have a non-negative minus a negative, ending up with a non-negative. Okay, that makes sense. Alright, so that's good. I'm just talking to myself to make sure that things make sense. So now we have the negation of y subscript n minus 1, and then d subscript n minus 1. Alright, so that's basically how it is defined. And this is a Boolean expression, okay? Because somebody is going to ask me, what are we doing here? Are we doing arithmetic addition? No, this is a Boolean expression. The overflow flag is a Boolean value. So the way we compute a Boolean value is a Boolean expression. So you have to make sure that you are using conjunctions, disjunctions, and negations here instead of the usual multiplication and addition. So that's basically how it's defined. And if you really want to add extra parentheses, you can always put in some extra parentheses around the conjunctions, because conjunctions have higher priority compared to disjunction. There we go. And if you want to say, well, but what about negation? I think negation only applies to the thing that's immediately to its right hand side. You would be correct. So if you want to have extra parentheses, it's kind of like you're going to a fast food place. You're saying, so what do you want to order? This is like, oh, I forgot about the negation on this one. Oh, good thing I checked. There's an exclamation here, exclamation point, which is negation. So this is how we compute the flag of overflow. So let's apply that. Okay, let's apply it once just to see, whether we have overflow being 0 or overflow being 1 in this case. Okay, so what do you guys think? First of all, what is n? How many bits are we dealing with in terms of the subtraction? This is a 3-bit subtraction because you can see x, y, and d, they only have 3 bits. So n equals to 3. So when n equals to 3, we are talking about x2, y2, and d2 over here. So we are talking about this digit, and also this digit down here. So the question is, what about the value of this entire expression? So when you look at the first conjunction, we are looking at the negation of this. So 0 becomes a 1, and this thing here, which is still a 0, and this thing here being a 1. So we end up with 1 and 0 and 1, which is a 0. So this entire term here is a 0. But then we have a second chance to make overflow a 1, which is evaluating the other side of the disjunction. So on this side, we have x2, which is a 0, and not y2, which was a 0, since it's negated becomes a 1. And then we also have the negation of d2, which was a 1, now it becomes a 0. So we end up with 0 and 1 and 0, which is still a 0. So basically, we have a 0 on the left-hand side of the disjunction, another 0 on the right hand side of the disjunction. So now we have 0 or 0, which is also a 0. So in this case, the overflow flag is a 0. Alright, so are we okay with this definition here and understand how to apply that to a binary subtraction? All right. Very good. And that's it. I think that's all we have to talk about today. Tonight is right on time. Kind of unusual for me. All right, so what we'll do now is I'm just going to release the activity, the lab for tonight. And let me get to right there. Subtraction and compare. All right, so I think I got the time all set up already, but I do need to take a look at the passcode because I cannot remember what passcode I have chosen to use. Now, one thing is I have set up most of the labs. If I forgot to do it to one of them, just let me know. I have set it up so that you can look at the answer after the due date. So this way you can also go back to the lab for review purposes. Okay, sometimes it's useful for review purposes. This one may not be as useful. So the access code is just flags. So I'm just going to copy and paste it into the text channel. So here we have flags as your access code, and you have until 9:50 p.m. tonight to get it done. So save and publish. There are 12 questions. They are related to the topic that we talked about today, which is binary subtraction. So I am also going to excuse me, sorry, I didn't mute the mic in time this time. Just happened too quickly. So anyway, I can totally. Oh, thank you, thank you. I'm not sure whether you guys want to bless an infidel. Infidel. Anyway, give me some spaghetti sauce. All right, so I'm going to save this one too, as a. Let me see. Should I? What should I do? What should I do? What should I do? I can always print it. Yep. All right, so I will just go ahead and print this to a PDF so that you guys will have access to the PDF. All right, so there we go. Gesundheit is the proper way to say something about sneezing for an infidel like myself. Yes, that is correct. There you go. Alright, so you have all the material that you need for tonight's lab. I am going to go get a few bites to eat. Just munch a little bit before I come back. So tonight's lab is a little bit interesting. Basically, there are only 3 types of questions. But for each type of question, there are 4 instances of those questions. So the first 3 questions is kind of repeated as the next 3, and then the next 3, and then the next 3. For certain fortunate individuals, you might actually see exactly the same questions. But for most people, you'll be seeing different questions. So there are 4 different types of the first kind of question, 4 instances of the second type of question, and 4 instances of the third type of questions. But once you know how to answer the first 3, you're just repeating the exercise for the next 9 questions, basically. So I don't think it's going to take you too much time, but I'm going to come back and respond to questions. I'm going to say respond to questions because as you guys might have noticed, I do not answer questions. I respond to questions with more questions. Well, that's kind of, I think that's going to be more helpful because I want you guys to find the answer. I don't want to give you the answer, but I want to give you something so that you can go find your own answer. That's why I respond to questions with more questions. Okay, Chris is right. Okay, Chris is right. I dance around the answers. But do you know how difficult it is to dance around answers? How much more work it is to actually not to give people the answer straight. Instead, diagnose what that person may or may not be understanding or may be misunderstanding, and then use a question to help that person to go like, oh, right, okay. That's actually hard. Okay, try doing that to somebody else. Okay, next time when somebody else asks you a question where you know the answer right away, try to respond with a question. Then you guys will start to understand the difficulty of doing that. Alrighty. Well, thank you. I'm pretty sure upsets, some people do not like it that way. But I think that's going to be useful and helpful in the longer run. Even though in the short run, it might be kind of like annoying. It's like, come on, just give me the answer. Alrighty. So I'm gonna step away for a few minutes, and then I'll be back to once again respond to questions. Alrighty. So if I don't see you again, I'll see you on Thursday. But I'll be back to answer questions. Alrighty. So let me get out of live.